Nah, it's okay. Okay, so you want to talk about number which number? 37. Good. How are you? Sure. Yeah. No, it's all right. Thanks for letting me know. You're, did what? Oh, okay. No problem, man. Thank you. Okay, so I'm starting class a little early so I can answer a few questions over homework. So 37, it says you're supposed to do parts A, B, C, and D. What part do you want me to talk about? B? G of F? Okay. So we're gonna be looking at part B, G of F, and they want you to state the domain of each composite function. And they want you to find what G of F is. So let me start with G of F of X. That's what G of F means, is to do that, which means you leave G alone and you plug F in. So we're going to plug F into G. Here's F. We are going to go into the G function, replacing every X we see with this. So it will turn into negative 4 over. Now I'm replacing that X with X over X minus 1. And then you have to do one more thing. You look at this as being negative 4 over 1 over X minus 1. And then you do the reciprocal. Yeah, you get rid of this down here and you put it next to this one flipped over. That's a very common thing in Cal 1 to do that. Okay? And so now this equals, and you are multiplying this negative 4 through the top now. So how about negative 4x plus 4, and then on the bottom, 1 times x gives you x. So this would be, that would be your composition. That makes sense to start? Any questions on that? 37 part B? Domain? Yeah, that's what we're going to do now. Okay? So now when we were talking about domains last time, what we said is, okay, in this problem you're going to start with x. X is going to go through the G function and come out as G of X. I'm sorry, it's going through F first, isn't it? Sorry. It's going through F first, then it's going to come out F of X. That's going to go through the G function. That will come out as G of F of X. Now we already know that when you send X through F, it comes out as X over X minus 1. And when you send that through G, what does it come out as? Everything we just got, right? At the end, negative 4x plus 4 over x. Okay? So what we talked about last time is trying to figure out what the domain of the composition is. So let's try and figure out what's our domain restriction as we plug a number here into the f function. So we're saying, what's the domain of f? So look at f. What can we not plug in there? 1, right? So I know right here for sure x cannot be equal to 1. Right? What I'm saying is this x cannot be equal to the thing that can't go into f, right? Then I get that answer, and that's got to get plugged in to the, I forgot to write G above here. It's got to go into G. So I want to know what this right here cannot be. And let's look at G. G, you can't plug in what? 0. So that means that this thing right here cannot be equal to 0. All right? It cannot be equal to 0. So I'm going to write that down. I'm going to write the x over x minus 1 cannot be equal to 0. Does that make sense? And now to figure out when this happens, what I do is I actually ask myself the opposite question. I say, if I want to know when something can't be something, then let me find out when it is, and then I'll just throw that answer out. So when is x over x minus 1 equal to 0? So how do we solve this equation? We're going to try and get rid of all fractions. So how about multiplying both sides by x minus 1? Okay, that'll clear the fractions on both sides of the equation. So I'm going to multiply the left side by x minus 1. I multiply the right side by x minus 1. Cancels out, right? On the left side it cancels out. On the right side, 0 times anything is still 0. So all we're left with on the left side is x. On the right side is 0. So we're saying that in order for this to happen, x is going to need to be 0, but we don't want that to happen, right? So we are going to make sure that we take 0 out of the domain also. So our conclusion here is then x cannot be 0. So in summary, the domain of this composition, the domain of g of f, we want to make sure that x is never 1 and x is never 0. And how do we say that in interval notation? Negative infinity to 0, make sure we go in order. Union, no, that's all right, 0 to 1, and then union 1 to infinity. The way I what? Took out? Mm-hmm. I set the f function equal to 0. Well, this is a different composition, though. This is g of f, not f of g, right? G of f switches the order in the order in which things are happening, right? It's an important point to make here. If this was f of g, then things would be different. Our first initial x right here would not be going into f, it would be going into g. So we'd be looking at g and we'd be saying, oh, it can't be 0, right? And then that answer, right, would be g, could not be equal to the domain restriction on f. So, does that make sense? Mm-hmm. Okay, I can bring those up. Do I see a hand raised? No? Okay. The last example I did, this was not really the last example. I think it was this one. Okay. So let me get back to the question. Here was the original function, right here. We were doing f of g. We did all this. You're okay with this part? Yes? Okay. So moving on to the next part, when we're looking at the domain, go ahead. Domain restriction on g, which is this. Well, I looked at both. Up here, I looked at both. I said, okay, on g, x can't be 5 halves, right? Yes? And on f, x can't be 2, right? But that's if we're looking at them individually. In the composition, it's a little different because when I'm looking at the composition, g, the only thing g is ever going to see is what we plug in, and that's x. And so we got to make sure that x can't be 5 halves. But what f is going to see is not x. F is going to be seeing this thing, This thing then cannot be equal to whatever f can't handle, which would be 2. Is this addressing your question, or? Maybe you were looking at it differently. Okay. So if you go back and you look at this problem initially, and look at them individually, you would think, okay, I can't have 5 halves and I can't have 2. Yes, individually I agree, but in the composition, you can't have 5 halves and you can't have 14 thirds. It's okay to have 2. See? Okay. You all right? Okay. Which one? Same problem? No. 41? Okay. Let me get back to today. For those of you who came in, I started a little early, and I forgot my tablet, my white table, so I have to sit here today. 41, and you want me to do f of g? Okay, so they give you the f of x is x squared plus 1. They give you g of x is equal to square root of x minus 1. All right, and we're trying to find part A, which was f of g. So we're going to figure out what that is. Then after we do that, we're going to figure out what the domain is. So f of g means f inside is g, which means f, and inside, let's write g down, square root of x minus 1. So we look back now at f. F has the x in it. We're going to replace that x with this entire expression, square root of x minus 1. So it'll look like this. The square root of x minus 1, but what? Square that, and then plus 1. So that is g being plugged into f. When you square a square root, it basically goes away. And then you get, oh, plus 1. The plus 1's still there, and your answer is just x. Now, this is actually an interesting question that we're doing here, because what we're saying is that if you start with x and you plug it in to g, then plug that answer into f, what comes out? X. And isn't that what we plugged in? So it starts out as x, it goes through these two functions and comes out totally unchanged. Does that make sense? We're going to talk about, that's what today is going to be about. Right? What happens when you actually have a function that when you put it together with another function, nothing happens? The end result is that you're back to where you started. So it's like 2 car washes. When you put your car in dirty, it cleans it, goes through the next part of the car wash, comes out dirty again, like exactly the way it went in, if that makes sense. That's a very special property of functions, 2 functions that do that. Yeah, let's now talk about domain, okay, because there are some domain restrictions here. So as far as domain, x first goes through who? G, right? G's first. It'll come out g of x. Then that answer is going to go through f and come out f of g of x. That's the picture of what's happening now. Specifically in this problem, when x goes through g, it comes out as square root of x minus 1. And then when that goes through f, we already know that that just comes out to be x. That was our end result. So we first initially talk about what are the restrictions going from here to here. So let's look at g and see what the restrictions on g are. Well, we can't have a negative under there, right? Can't have a negative. So up here with g, just looking at g, I know that the x minus 1 can't be negative, which means it must be greater than or equal to 0. Now this is an inequality, so it's solved differently than we do with an equation. We can move the 1 over to the other side by adding it, right? And you just get x is bigger than or equal to 1. And that's so far, that's our domain restriction. We have that the x that we plug in has to be bigger than or equal to 1. As long as that's true, we're good to go. Now, what about going from here to here? So looking at f, is there anything that f can't handle? Well, f is x squared plus 1. X squared plus 1 does not have a square root in it, doesn't have fractions in it. There's no real issue for us. F can handle anything. So regardless of what gets spit out here, right? Regardless of what gets spit out, this domain is everything. So I'm just going to, how do we say everything? You could say negative infinity to infinity. I use this double struck R to represent all real numbers. So whenever you see that, that means there's no problem, right? So our only domain restriction is what? That one right there. X has to be greater than or equal to 1. So the domain of this composition is that x is greater than or equal to 1, which in interval notation, oh, that's wrong, is bracket 1 to infinity. Everything from 1, including 1, so that's why I'm using the bracket all the way out. You could say x is an element of this set, or you could have used set notation, which we really didn't use a lot of. This one right here. The set of all x is such that x is greater than or equal to 1. Okay. Forty-five. Yeah, you know what? Let's do 45 because that's kind of going to lead us right into today. All right. On 45, you were given two functions, f of x equals 2x and g of x equals 1/2 x. And they wanted you to show, okay, these were the instructions. It said show that f of g of x is equal to x, and show that g of f of x equals x. It's like a what? Yes, we have to show it's true. Okay, they want us to prove that. So we just need to start with this left side right here. Start with that and show it equals, at the end, show that it equals x. And then we'll go do the other one. We're going to start with the other one and show that that one works, and that turns out to be x also. All right? That's what they want us to do. So let's do it. Start with f of g of x. By the definition, this meant f, and inside goes g. And then that means f, replace g, with g, replace g with 1/2 x, because that's what it is. And then you're going to plug that in to f. So what do I get when I plug that into f? 2 times 1/2 x, right? So I'm just replacing this x right here with this whole expression. So that's it. And what's 2 times 1/2, or what's half of 2? 1, so that's just x. Check mark, meaning I showed the first thing, didn't I? I showed that f of g of x turns out to be x. Now let's show the other one. G of f of x. Notice they're not asking for domains, are they? No, right? They don't talk about domains at all. They just want you to show these two things. So this means you start with g, and this time you plug f into g. That means I'm going to start with g, replace f with what? What's f? 2x. And now I'm going to go to the g function. I'm going to replace this x right here with 2x instead. So it'll become 1/2 times 2x. And then half of 2 is 1 again. You just get x, and that's the same thing. And you'd be done at this point. Yeah, but like I said, this is about today. If you have two functions that when you put them together, f of g, and you get x, and when you put them together, g of f the other way, and you get x, those functions are very much connected to each other. They're what we call inverse functions. Do which one? I'll do 43, but I'm going to work fast. I don't want it. Well, which one though? Because you're asked to do f of g, g of f of f, and g of g. So which one do you want me to do? F of g? Okay, so we'll start with this. F of g of x means f, replace g with x plus 2 over x minus 3. And this we saw last class got pretty ugly because you're going to be taking this, right? That's your g. You will be replacing every x in f with this fraction. The algebra gets kind of ugly. So I replace the top left corner, x plus 2, x minus 3, but next to that I have minus 5. Over, bottom left corner is x plus 2 times x minus 3, and then plus 1. Okay, so that's f with x replaced with g. And that's a complex fraction. And so we need to put this all together and simplify it. So what did I say you have to do here? Anyone remember? Get common denominator, top and bottom. So we're going to look at this 5 in the top right as a 5 over 1. I'm going to multiply the top and bottom by what? X minus 3. I'm going to look at this 1 on the bottom as a 1 over 1. I'm going to multiply top and bottom here also by x minus 3. Is that clear to everyone that we can do that? I will distribute the 5 through. I'll distribute the 1 even though that doesn't do anything. And I'll just rewrite the whole thing. X plus 2 over x minus 3 minus 5x minus 15 over x minus 3 over x plus 2 times x minus 3 plus x minus 3 over x minus 3. You know, sometimes I see students, they'll do this. They'll get through this whole part like this, and they're all good. And all of a sudden, they'll be like, okay, and this cancels, and that's a 1. Which means you're right back where you were, right? I mean, the whole point of you putting it there was so that you could put things together. So don't lose sight of what you're trying to do. Okay, so now I will combine these two together. I will combine these two together. I have to pay attention to the sign in the middle. That negative must distribute to both of those. Okay. So we'll have x plus 2 minus 5x plus 15 over the common denominator over, now x plus 2 plus x minus 3. So I don't have to worry about distributing a negative on the bottom one, right? And then all of that over my common. I'll clean up the numerator on the top here. So x, let's take away 5x, negative 4x plus 17 over the common denominator, x minus 3, and then 2x minus 1 over x minus 3. And this is where you flip it, okay? Did anybody watch Usual Suspects? Not yet, huh? Flip it. Well, I don't know if it's The Usual Suspects or Usual Suspects. I don't know. I'm going to do a bonus question off of that. Yeah. Okay, so I took the fraction, I flipped it, right? And now I can do what? I can cancel this x minus 3 and x minus 3, which will leave me a final result, negative 4x plus 17 over 2x minus 1. No, you're good there. Yes. That's right. Yep. It's all because we had multiplication right there. That dot. Okay, now domain. So for the domain, I'll start a new page. We had x going through G first, then G going through F, which gave us f of g of x. So that means x went through G first and came out, what was G? X plus 2 over x minus 3. Then that went through F, and if we did everything correctly, it should be negative 4x plus 17 over what? 2x minus 1, okay? So that's the chain of events. So let's first talk about what restriction do we have taking something and plugging it into G. Can't be 3. X cannot be 3. Now, when we take something and plug it into F, what can we not plug into F? So let's go look at F real quick. Here's F. What could not be plugged into F? Negative 1, right? So that means this can't be negative 1. But what can't be negative 1? The entire thing here that's being plugged into F, right, cannot be equal to negative 1. So I get x plus 2 over x minus 3 cannot be negative 1. That makes sense? So now I go ask myself, well, when does it happen? When does x plus 2 over x minus 3 equal negative 1? And then whatever that answer is, I'm going to throw it out. So how have we been doing this? Multiply both sides here by x minus 3. Good. And on the left, they cancel. On the right, it does not cancel. Remember last problem we did? It was 0 on the other side, so it just wiped out to 0. This does not wipe out. This actually has to distribute through. So what do we get? Negative x plus 3. This is a linear equation. You're solving for x. Let's move all your x's to one side, all your numbers to the other side. So how about we add x to both sides like this? Subtract 2 from both sides like that. What do we get? 2x, careful, 2x equals 1, so x is a half. And that's what x cannot be, right? That's what x cannot be. So our conclusion here is that x cannot be equal to negative 1/2, to 1/2. So our domain of that f of g was that x could not be equal to, what was it up here? 3, right? We said it couldn't be 3, and x couldn't be a half. And then we set up our interval notation for this. Yes? Over here? Yeah, I know. We talked a little bit about that last class, that there's a danger in that because sometimes you'll, well, it was the last one I did, last class. Yeah, or if you have more than, this was an example here where when you take x squared and square root of x and put them together, you get x. And if you look at the domain, you look at the domain of just the answer. Just go over here and tell me, is there any domain restriction? No, right? But there's domain restrictions. There are domain restrictions for this problem. So just looking at the answer is dangerous, okay? Or else I would just tell you to look at the answer. That's right. It'll work for this problem, but not for every problem. Yep. Yeah. What's wrong? You don't want to just keep finishing this off or what? Okay. Yeah, I mean, I, I'm trying to give you a way that's going to work, and it won't get you into any trouble. So when there's shortcuts and things like that, I will give them to you, you know, but I would hate to give you this and say, but there are certain cases, and then you'd say, well, how do I know if there are those cases, if that's the case I have? And I'd be like, well, every case is different, so I wouldn't be able to give you like a rule. It would be like the stupid English rule of I before E except after C, except after whatever, except when it sounds like, it would just be a mess. You know what I'm saying? Yeah, you know what I'm saying? Yeah, okay. All right. Okay, so let's move on to today's stuff. No clicker. Yeah, I'm kind of clickerless now. No, I don't know. 6-2. 1-to-1 functions. That's not a J. It's a semicolon. Inverse functions. Yeah, I've fallen a little behind on things. You know, I've been trying to keep up with notes in this class and stuff, and fallen a little behind because midterms. You know, I gave 6 midterms and had to grade them, and I still have 1 stack left, and so yeah, it's not fun. It's my fault for scheduling them all in the same week, but okay. One-to-one functions. So let me give you an example of a function that's not one-to-one first, and then we'll contrast it with one that is. So look at this. Look at this example of function f of x equals x squared. And what I'm going to do is I'm going to draw a picture of inputs and outputs. So I'll just put in here, out here. Okay, so let's plug into this function 0. What comes out? 0, right? Plug in 1, what comes out? 1 squared is 1. Plug in 2, what comes out? 4, okay. Now, if I plug in -1, where does it go? 1. I plug in -2, where does it go? 4, right? So I want you to notice something here. It's probably pretty obvious to you. But there is an output on the right side that actually comes from 2 different inputs, right? Do y'all see that? Another way of saying that is that if you take 2 different inputs, in this particular function, you are not guaranteed 2 different outputs. You actually have 1 and -1 going to the same place. So let me draw it in a different way that might make a little more sense. -1 and 1 both go to the same value of 1, don't they? And that -2 and 2 both go to the same value of 4. Do you see that? This is not a one-to-one function. A one-to-one function, every single input goes to exactly 1 unique output. And the next input that you have will go to a different output. They never go to the same one, okay? So I gave you an example, not one-to-one. Not one-to-one. I'm sorry? Yes. Yep. So this is not one-to-one since f of 1, f of 1 equals f of -1. Do y'all see that? If I plug in 1, it's the same as plugging in -1. Yes? Okay. So what does it mean then to be one-to-one? For a function to be called one-to-one, any 2 inputs, different inputs correspond to two different outputs. Okay. Can you make sense out of that or no? This is what it means to be one-to-one. If you take any two inputs that are different, 1 and -1, then those two inputs correspond to two different outputs. 1 and -1 cannot go to 1. They have to go to two different things. So here's the way the book likes to say it. So this is another way of kind of phrasing this. If x1 does not equal x2, okay? So you know how we plug x's into functions, right? So let's say we pick an x and we call it x1. We pick a different x, call it x2. So if you have two different numbers, right, and you plug them into the function, then what I can guarantee you is that if you're one-to-one, the answers will not be equal. Okay, so that is basically what it means to be one-to-one. Two different inputs means two different outputs. The outputs will be distinct from each other. They won't be equal. A lot of times if it needs to have like a squared in it or something to make it, or like even the absolute value function would not be one-to-one, right? But that's not a squaring function. So, okay, so let's get to an easy way to see if a function has an inverse. Okay. It's called the horizontal line test. The horizontal line test. If you are given the graph of a function, okay, so somebody gives you a graph of a function, right? You're looking at it there. Visually, you're just looking at the graph. So if you're given the graph of a function, and every horizontal line hits it no more than one time, then it is a one-to-one function. All right, so let's do some examples. I'm going to give you a graph. That is a parabola, isn't it? Is that a one-to-one function? So to be one-to-one means every horizontal line that I draw, every one that I could possibly draw, hits it no more than one time. So here, I'm going to draw a horizontal line right here. Does that hit it more than one time? No. How about this one? Does that hit it more than one time? Yes, it hits it twice. As soon as that happens, it is not one-to-one. Right? That's it. It's not one-to-one. And the way to think about it is, look, there's two inputs. There's an input over here that when you plug that in, it spits out a value that's this high, right? But when I plug in an input over here, it spits out the same value. So I have two different inputs going to the same output, the same height. So that's why the horizontal line test works. Here's another example. Let's take a polynomial function, something like this. Scroll up. Is that a one-to-one function? So every horizontal line that I draw, does that hit it more than once? No, it just hits it once. Does this hit it more than once? No. Does this hit it more than once? No. Any line I draw, is it going to hit it more than one time? No. This passes the horizontal line test. This function is one-to-one. So the answer, I forgot to put the answer here. No, yes. All right. One-to-one. Oh, and sometimes instead of writing one-to-one, we write 1-1, one-to-one instead, when we want to be lazy. You know, does this make sense? Do you remember the vertical line test? It's the opposite of the vertical line test. That's all it is. Is this one-to-one? It's supposed to be a circle. There. Is that one-to-one? Yes. All right. Hold on. It's not even a polynomial what? You said function. It's not even a function, is it? Right? It fails the vertical line test. Now that's important because look at what I said here for the horizontal line test. If you are given the graph of a what? Of a function, and every horizontal line test, then it's one-to-one. So this one right here isn't even a function. So it makes no sense to talk about whether or not it's one-to-one if it's not even a function to begin with. So the answer would be no, but it's no because it's not a function to start. I'll show you a classic example of something that gets students on a test. Is this one-to-one? So you start drawing horizontal lines, right? You draw your horizontal lines and you go, okay, yeah, it doesn't hit it more than once, doesn't hit it more than once, doesn't hit it more than once, and you're all happy about it. You're like, yep, it's one-to-one. But it's not a function. So you can't tell me that a function is one-to-one when it wasn't a function to start. So the answer for this would be no. It's not one-to-one because it's not a function. What would be the question on that? Is this one on a test? Most likely, what I'll ask is this a function? Is it one-to-one? Two different questions, which will help you because if it fails to be a function automatically by default, there's no way it's one-to-one. So has to pass both. That's right. So this would be not a function. This one, not a function. So not one-to-one, obviously, not one-to-one. It's like me saying this. What color is this car? It's not a car. Okay? So you can't say, you know, is this function one-to-one and what you're looking at is not a function. Doesn't make any sense. So yes, it's not one-to-one, but hold on, it wasn't, you know, wasn't a function to start. So all right, I hope that makes sense. All right, so if someone gives us a graph of a function, I think hopefully you would agree it's relatively easy to be able to determine if it's one-to-one by looking at the horizontal line test. Would you agree? Yeah? Okay. But what if you're not given a function, you're not given the graphical representation of the function? What if someone just gives you the function, f of x equals x squared? How can you tell if it's one-to-one, right? Yes? One input, one output, right? Let me try and follow the book here a little bit. All right. I need to give you a definition first. This is the definition of inverse function. Suppose f is a 1-to-1 function. That means that if I plug in an x, it goes to a y, right? And this is unique. Meaning that if I plug in a number, it goes to a unique number. There's no other number that I can plug in over here that would go to the same place. Does that make sense in that picture? I plug in an x, it spits out a y. The process of going from left to right, I'm using the function f, right? F transforms this x value into something over here. Now, yes, you could call this f of x, but I'm calling it y right now. Is that all right? So if you have a 1-to-1 function, you know that for that specific x, it goes to a unique place. No other value of x will get you there, which means there must be a way to get back. Because when I go backwards, I only come from one place, right? So what we want to define here is the function that takes you backwards. Okay? That function would take you back. I should draw it like this. Takes you back, look at man, to x. From y back to x. That is a function that takes you backwards. And it is called the inverse function. And we have a special notation for it. It's f with the little -1 written on it. A little -1 exponent. So suppose f is a 1-to-1 function. Then there exists another function written which is called its inverse function. It's the function that undoes the function f. It's the car wash that makes the clean car dirty again. All right? That's what it is. I'm sorry? Yes. Yeah. Uh-huh. This one? Are you talking about this one? Yeah. So look, think about these two functions. This function f doubles whatever you plug in, right? It doubles it. And then the g function does what? Halves it, right? So doesn't halving something, isn't that like the opposite of doubling it? Yes? So these two would be inverse functions, but we have to show that. But yes, that's kind of where we're going. Get you back there, yep. So here's another picture for us. We started, when we started talking about functions, we talked about f doing this, right? Starting here, and you said over here was the domain. I would call it dom of f, right? That's the domain of f. So you plug these things into f, and it spits out these things, and this was called the range of f, wasn't it? Sometimes we just say ran f instead of range. We just write ran, so I'm going to do that so you can say you've seen it. Ran f. That's the range of f. But if f is 1 to 1, then there's a function that goes the opposite direction, yes? That function would go backwards like this. And now the range of f, oh, I should label this f with a little -1. This range of f is actually the what of this? The domain of f inverse. And then over here, the domain of f actually becomes the range of f inverse. So they switch spots, if that makes any sense. You could also write it this way. The domain of f is equal to the range of f inverse. These two sets are the same, aren't they? The set of numbers you can plug into f is equivalent to the set of numbers that comes out of its inverse. The set of numbers that comes out of f is the same as the set of numbers that goes into its inverse. So you could write that, and that the range of f is equal to the domain of f inverse. So this entire note right here is all together, okay? We were assuming f had was 1 to 1, which meant it had an inverse. If that's the case, then these two things are true. All right, next note. How to verify two functions are inverses. You must show two things. One, f of g of x equals x, and second thing you must show is that g of f of x equals x. So if somebody gives you two functions and they say, hey, are these inverses? Like the 2x and the 1/2 x? This is what you have to do in order to show that they're inverses, or that they are inverse functions. So why do we show that? Let's see if we can draw a picture real quick. What's happening here is that what we're trying to show is this. If I start out and I plug an x in, I plug an x in to g first, it comes out g of x, right? So that's, I'm doing this fog one, right? X goes into g first. Then that goes into what? F, and comes out unchanged, which means that it takes it back to where it came from, and that would be f. If that happens, if your x turns into g of x, and then that g of x gets taken back to x through f, if that loop happens, then the inverse relationship is there. But you also need to work the other way. You need to work where if you start with x and you go through f first, and then comes back to x, that the g is what takes you back. If both of those things hold true, we have found the inverses, or the inverse of a function. By the way, inverse functions are unique. So if you find an inverse function, there is not another one. It's the only one that'll take you back. Okay, let's do an example. Are these inverse functions? Question. f of x equals 1 over x minus 1. G of x equals 1 over x plus 1. So if I were to plug something into G, spit that answer out and give it to F, will it come out to what it started as? So let's just try something and see if it works. Let's plug 1 into this one. What happens if I plug in 1? What does it spit out? 2, right? Plug 2 into this. What happens if you plug in 2 here? Get 1 over 2 minus 1, you get 1. So wait, we started with 1, plugged it into G, got 2, plugged that answer into F and got back to 1, didn't we? Okay, let's try it the other way around. Unfortunately, we can't plug 1 in here though, can we? So let's plug 2 into this. What happens if we plug 2 in here? We get 1. What happens if we plug in 1 into this? We get 2. Yes? So we started with 2, went through here, became a 1, that went into here, became a 2. So it went back to where it came from. All right, but let's do it the way you have to do it on a test. We have to say 2 things. First, show that this is x. Okay, let's show that that's true. So I'm going to take F. Inside of it, I'm plugging in G. And notice I'm working just with the left side right now. I'm just saying, I'm trying to figure out what this is equal to. What do I need it to be equal to? X. Okay, let's see if that happens. Replace G with 1 over x plus 1. Go with me? It's just like you did in your homework. Now plug that into F. So I will replace this x in the bottom left corner of F with this entire expression right here. So you get 1 over, bottom left corner becomes 1 over x plus 1, but then what's still down there? Minus 1, right? So here's the x got replaced, right? Okay, let's try and clean this up. What can we do in the denominator? We can cancel those 1's out, which means you just have 1 over x, but what's 1 over x? So flip the bottom up, and you just get x over 1, don't you? Which is just x, which is what I wanted to show, right? I wanted to show that was true. What about the second thing I need to show? What's the second thing I need to show? The other way around. G of f of x is x. It is not enough on a test to show just one. You have to show them both. So G inside of G is going F. So G inside of that is going, F is 1 over x minus 1. And that's getting plugged into G. So 1 over x minus 1, but then plus 1. Does that make sense for G? G was 1 over x plus 1. So I'm replacing the x with 1 over x minus 1. What do you want to do here? Invert this. 1 over x minus 1 is just x minus 1. Then you still have plus 1. What happens? X's cancel. I mean, 1's cancel, and you get just x. And that verified. We okay? Oh, no, I said, are we okay, like the class. But are you okay? I'm just messing with you. Okay. Example. Inverses or not? You tell me. F of x equals 2x plus 1. G of x equals x minus 1. So what do you have to show first? Show f of g of x equals x. Try it yourself. See if that works out or not. What's f of g of x? 2x minus 1? Is that what you get? So what? It's not x. That's not x, which means they're not inverses. Doesn't matter. You don't even have to do the other one. You're done. This is not equal to x. No, they are not inverses. Yes. Do the other one? No. No. Nope. As soon as one of the two conditions fails, you're done. If one of the two conditions holds, you have to check the other one. So this goes to show you that, obviously not every function, every two functions you put together are inverses, There should only be one function that does it. The question here would be, and we're going to answer this question right now, if this function was not the inverse, right? This did not work, what does? And do we have a systematic approach to finding it? Do you understand what I'm asking? Like, it's one thing if I give you two functions, say, are they inverses? And they turn out to be inverses and you're all happy. But well, you're probably not happy, but you know what I'm saying, right? But what about I just give you a function, you're like, hey, I need to come up with the function that undoes this function. That is more valuable to us. So how do we do it? Before I do that, let's talk about what we're going to need to happen. So if we are given f, which is 1-to-1, which means it has an inverse, okay? If we are given f, which is 1-to-1, how do we find its inverse? All right, so let's see if we can make sense out of this. Drawing a picture. Again, these pictures. I want to take a look at what happens here. When I pass my x value through f, I need to take that y value and I need to send it back where? If this is going to be an inverse, it's got to go back to x, right? The function that I'm looking for, g, which I'm highlighting here, the one that we're trying to find, right? What is that? Has the characteristic that it's going to take y and send it back to x, right? Y is going to become x. No, just y is going to become x. Just keep that in mind. F turns x into y. The inverse function that we're trying to find turns y back into x, right? Turns y into x. Now I'm going to give you the steps, and one of the steps, when I get to it, I'm going to say, why are we doing this step? It's related to this picture, all right? So here are the steps. Steps. First thing, and remember, you're given in the problem a function, all right? You're given f of x, a function of x. The first thing you'll do is you'll replace f of x with y. The second step, you'll swap x and y in the equation. And the third step, you'll solve for y. And the fourth step, you'll replace y with f inverse of x. Okay, so it's a four-step process that we're going to do. You ready? All right, let's begin with this one. Did I move too fast? We got all the steps? How about the function we were just trying to do that it didn't work out? One of them was it 2x plus 1 or minus 1? 2x plus 1, right? We couldn't, this g was not its inverse, so let's find the inverse of this. So here we go, solution to this. First thing, is f 1-to-1? You tell me, and tell me why it is or is not. What is it? It's a line, right? It's a line. That's a line? Isn't that a line? So if that's a line, does that pass the vertical and horizontal line test? Yes. Since that's a line, it's 1-to-1, right? If it's 1-to-1, it has to have an inverse. No, it means that all linear equations are, but they're not the only ones that are. All linear equations except a vertical line, which would not have an horizontal line, which would not have an inverse. Yes? Y'all okay with this? Okay. So all non-vertical and non-horizontal lines have inverses. But if they're vertical or horizontal, you have issues because it fails either the vertical line test or the horizontal line test, one or the other. So whenever we're looking at a function, we first need to make sure it's 1-to-1 because that's what guarantees us the inverse exists. So the answer is yes. And now we go through the process. First step, I'm going to do what? Replace f of x with y. So I'm going to rewrite this thing, except it's going to look like this. Y equals 2x plus 1. That's the first step. Second step is to do what? Swap the x and y. That means I want my y to become an x, and I want my x to become a what? A y. Why is it that I want that? Why am I doing this step? That's what I was trying to show you with this. Is that if f takes x to y, then g is going to make your y turn into what? X. So that's what I'm trying to force to happen here. I'm trying to I'm trying to force my y to become an x. And of course, my x also has to turn into a y. So they're switching places. That's the effect of an inverse. It takes it back to where it came from. So now the third step is to solve this equation for y. That means you have to isolate the y, get it by itself on one side of the equation. So can you get that y by itself? Okay, so how do you do it? Divide 2, but what's first? Move the 1 over first. So subtract 1 on both sides. And then divide by 2. And just divide the whole thing by 2. Does everybody follow that? The fourth step is your final step, is to replace the y with what? F inverse. I claim that that's the answer, and I'm going to write it a different way. We never really like to write the inverse on the right side. I'll just rearrange. I'm claiming that that's the answer. How could you check it? Now, on the test, if I ask you to find the inverse of a function, what I will do is then ask you to verify it. So now you have to say f of g of x and g of f of x. However, we don't have g. What are we calling this? F inverse, right? So here's my checking work. All right, now I'm going to check it. I must show two things. I must show, first of all, f of, now be careful, not f of g, because I didn't call it g. I want to show that f of f inverse of x equals x. And then 2, I want to show that f inverse of f of x equals x. So I'm using, instead of g, the little f inverse. Okay, take out a sheet of paper. All right, put your name on it. This will be a group quiz. I want you to show those two things using, right, this is f inverse. F was given in the problem as 2x plus 1. I want you to show that f of f inverse of x is x, and show that f inverse of f of x is x. For this problem right here, yes. So I'm asking you to finish this. I'll write down in the top right corner what our results were. We had that f of x was 2x plus 1. We had that the inverse function, we think, right, we're checking right now, we think it's x minus 1 over 2. So work together, all right? I'll give you about 10 minutes. See if you can come up. I mean, you'll know you have the answer, right? Because you'll show it equals x, and then you do the other way, and you show it equals x, and then you're done. That's the good news with this. So you know you've made it. Yeah, plus or minus 3 or 4, I think, is probably. Yeah. Okay, we good? Everyone's turned in? No questions on that? That was a relatively easy function to find the inverse of. They get, as you might imagine, a little more difficult. Maybe we should try one that's a little more difficult. I'm sorry? This is not another quiz, no. But I'd like for you to start this one out in your groups. I want you to see if you can find the inverse of this, because I want you to see the challenge. No, my cursor's still there. Ha ha ha. Yeah, that's an I. What are you going to do with that? No. Okay. Try and find the inverse. Go through the 4 steps. Let's everyone assume it's 1-to-1, that the inverse does exist. Okay, assume that, and now go through the 4-step process and see if you can find it. And I think you're going to see how the algebra of this one gets ugly. This is a test problem right here. Okay. If you want to talk about like what type of problem I give on a test, this is one. Find the inverse and verify. But I would say find the inverse and verify. But right now, I just want you to find the inverse. And we'll see when people start getting stuck. Is it? Yeah, I would say, verify this inverse if it exists or something like that. Because it may not. Yes. That's it. That's right. All the x's become y's. All the y's become x's. Y'all good? Y'all know what you're doing? Yeah? Did you get it already? No. This is. I want y'all to start on this one. I want you to try and do the 4-step process on this. No, you don't need that. No. Different problem. Yes. Can't cancel those y's. You see the problem, right? You see this is going to be. I just want you to play with it for a few minutes. Nope, can't cancel the ones because nothing cancels because they're separated with addition and subtraction. So what you're trying to do is solve for y. The question is, how are you going to do that? And so let me see what you do. 1/1. Yeah, on both sides. Sure. I mean, go for it. Try something. Try something, and then I'll show you the way. Oh, no, we're doing the 4-step. Hold on, you're not there yet. Oh, wait, you're right here. This step right here, you got to solve for y. That's the step that's tough. You're kind of on the right track there, but you need to work with the equation. You have an x on the left side, right? There's an x on the left side of that equation. Work with the equation. Oh, okay. Sorry. Not so nice, is it? Give it a few more minutes. Give everyone maybe about another minute and a half to look at it. What did you do? Multiplied the... Both what? Top and bottom? You multiply y minus 1 on the right side? Is that what you did? You're trying to get y by itself, right? Anybody think they're close? Yeah. This isn't a quit. Like a long division or something? Yeah, that might work. No, because you're going to have a remainder. No, you'd worry about it. You'd have to account for it. It's a good idea, but it's not going to work. Hey, man, that's the way you have to do things. You got to try. You got to try different things. No, hold on. This first step is right. Okay, your first step is right. But after that, there's where you can't subtract a y here until you take it out of the parentheses first. But you're on the right track. Okay, look, because we only have 15 minutes. Okay, everyone, please pay attention to me because this is like I said, this is like a test problem, all right? The algebra required in this problem is slightly above what, this is like real algebra stuff, okay? No, it's like a test problem. It's not the test problem. Okay, what's the first step? Replace f of x with y, right? Okay, that's your first step. Second step is you swap x and y. What that means is everywhere you see a y, you put an x. Everywhere you see an x, you put a y. I believe by walking around most of the tables, everyone was at least there, right? Okay, now, you're trying to get y by itself. The trouble is that y appears both in the numerator and denominator here. You cannot cancel out ones or you can't cancel y's. You have to get the y out of there and get a y by itself on one side of the equation. Multiply both sides of this equation by y minus 1. That is going to have the effect of clearing the fraction. So that's what we're going to do first. We're clearing the fraction out. Okay? See, I'm working with it like an equation, both sides of the equation. On the right side, what happens to the y minus 1s? They cancel out. Okay, so those are gone. On the left side, I have what I have. I have y minus 1 times x equals the right side, which is 2y plus 1. Y'all okay up to there? Now, what you might be thinking right now is, hey, I almost have y by itself. I just need to move the 1 over and then divide by 2. The problem with that is you have a y over here also. You cannot tell me you've solved for y if y appears here and over here. It's not going to work. So what we're going to do is we're going to distribute the x through first. Okay, distribute the x through, and this is not necessarily the most natural thing that you want to do, because you might think I just made it look worse. Okay, but what you've done is you've freed the y from the parentheses, haven't you? So now what I'd like to do is I'd like to take everything that has a y and move it to one side of the equation, everything that does not have a y to the other side of the equation. So I'm going to leave the xy here, and I'm going to bring the 2y over, which makes it a negative 2y on the left. And I'm going to take the x, which doesn't have a y, I'm going to add it to both sides, and it'll appear on the right side. See if that makes sense to you. So I have x minus y minus 2y equals x plus 1. Do you follow me there? Just moving things on, all y's to the left, everything without a y to the right. Are there any questions on that step? You sure? What are we trying to solve for? Y. Why is it that I would put all my y's on one side and then anything that didn't have a y, take it to the other side? What? Because you can actually factor a y out of the left now, can't you? These both have y's in them, right? Pull the y out. If you pull the y out, what are you left with? X minus 2 there, right? Equals x plus 1. We're almost there. Since this is multiplication between the y and this parentheses, if I want the y by itself, I divide out this entire factor on both sides. And when I do that, I'm done. So I'm going to divide both sides by x minus 2, divide by x minus 2. They cancel here. I'm left with the y equals x plus 1 times x minus 2. There it is. Wait, hold on. Yeah, so now now is the third step was solving. The fourth step is to replace. So fourth step would be to rewrite that as f inverse x equals whatever we just got. X plus 1 over x minus 2. Now, I did not ask you to check, but that would be your next step, wouldn't it? You would check it. Now, I'll just trust that you could check that on your own. But there's always one good way that you can check it. It's not the same as checking it by showing f of f inverse of x equals x and f inverse of f of x equals x. But it should at least work with any number you pick. Just one example, it should work. So let me see if I can pick an easy example. Let me try and plug 2 into this. Okay? In my head, let's plug it in. 2 times 2, 4 plus 1, 5. Okay? 2 minus 1 is 1. That's why I chose 2, because 2 minus 1 is 1, and that would make it easy. Does that make sense? So when I plug 2 into this, right, it spit out 5. When I plug 5 into this, it should spit out 2. Plug 5 into this. 5 plus 1, 6. 5 minus 2, 3. 6 over 3, 2. So am I sure they're inverses? No. Do I feel good that they are? Yes, because the chances that I got it right, or got it wrong and that worked are very slim. Okay. Yes. No, I would want you to do f of f inverse of x equals x and f inverse of f of x equals x. Yep. Okay. But look, I mean, that's putting this function together with this function is what your homework was over last time, right? I mean, that's like I did that, right? You asked about number whatever it was. I mean, it was 2 fractions like that, and you had to put one in the other one. So, okay. Awesome. I think that that's enough for today. I don't want to start the next part. We have 10 minutes. Let me tell you what homework you should work on. It's Easter weekend, so I'll give you an extra amount. No, I'm kidding. All right, so I'm going away from what's on your schedule. Just do what I'm about to tell you. Page 418. (19) through 24, all. Now those problems are you look at a picture and you tell me if it's one-to-one or not. So those take 5 seconds each. Then 33 through 41 odd. Let's do 51, 61, 63, and 67. Okay, so 31 through 41 odd. Oh, these, yeah, that's good. 31 through 41 odd. These, you have to show that 33, sorry, 33 through 41. Those you have to show that f of g of x equals x and g of f of x equals x. So you have to show fogging off both ways. 51, 61, 63, and 67 are just finding the inverses. That's what you just did right now. All right? You don't have to verify it. All right, everyone, have a good holiday. Campus is closed tomorrow, so just FYI, I won't be here.